So a delay line is often implemented in software using a circular buffer. So a circular buffer can be seen as a type of high performance FIFO queue, a first in, first out, and it's also called a ring buffer. And we can see that there is this definition of circular buffering on this data sheet from another processor by Texas Instruments. So the circular buffer uses pointer manipulation to add new samples to the buffer by overwriting the oldest available samples, reusing a memory buffer. So when the pointer reaches the last location of the delay line, it needs to drop back to the beginning of the line. So this would normally involve some amount of software overhead, and when a circular addressing is used, the pointer automatically drops back to the top whenever the bottom of the buffer is reached. So as a consequence, the memory locations appear to be tied together in a circular manner, hence the name circular buffer. And most digital signal processors implement circular buffering in hardware in order to conserve memory and minimize software overhead. For this example, we are not going to use circular buffer in hardware, but we are just going to use the circular buffer in software. So here we are going to implement a basic delay effect in Python using the circular buffer, but this is a very non-Pythonic style. There are many ways how we can implement this in Python, much more efficient than what I'm doing here. But I'm using this kind of implementation because I want it to be closer to the way I'm going to implement in C to program our DSP. So here we are defining some parameters, the sampling frequency, the delay time in seconds. Then I'm converting the delay time in seconds to the delay in number of samples. Here we are creating a buffer with the length of the number of samples we want to delay. And here is an index, so it's something similar to a pointer. Here is the circular buffer itself. So we are using the buffer, so we define it as global variable, so there's a buffer and this index. Here the output is equal to the buffer at the index used by this pointer. Here we are setting the buffer to be equal to the input. Here we are adding 1 to the pointer, so the pointer goes from 0 until the end. And here we have two ways how to set the pointer back to the beginning when it reaches the end. So here we are using an if, so if the pointer is bigger or equals to n, the pointer is equal to the pointer minus n, or we can use the modulus operator, and then when the pointer is equal to n, it will go back to 0. Now we have our basic delay. So here we have our dry mix gain, the wet mix gain, the feedback loop. Here's our input. We're also using the buffer and the index. We are setting an after delay equals to 0. So this after delay is a signal after the delay line. So here, and it will start with the value 0. Then we are setting before delay. Here we are setting just for this example, we are defining an empty list, and we are going to append the output to this list, so we can have our final audio and listen to it. Here before delay is the signal just before the delay line, so it's here. So it's the input signal plus the after delay times the feedback. So this is what I'm calling the before delay. We have here, so it's the input plus the after delay times the feedback gain. Then the after delay is the circular buffer of the before delay. So it's basically the after delay is the delay line applied to the before delay. And the output will be after delay times the wet gain plus the input times the dry gain. So we have here is the input times the dry gain plus the after delay times the wet mix gain. and then we are just appending to this empty list so that I can have here our delay and listen to it. So here I'm applying this basic delay to the delay input. Is the same we used here. So this is the input signal, and now I apply the delay, and this is the output. So we see is the same output as before, but now when I run the cell, you see I'm running. First I need to run the previous cells, and it's much faster than the filter version that we had here. It took much longer. Here we just run, and that's it, it's already calculated. So we are going to use this kind of implementation, but adapting it to the C language to program our DSP.